Next, I want to talk about what we do as a business at Boltz and how we use the latest and greatest features of Bitcoin and elements. And yeah, let me switch the presentation real quick. So at Boltz, we have one mission. What we want to do is connect the different Bitcoin layers. Be a bridge in the Bitcoin ecosystem so that you can move your coins free and as fast and efficiently as possible between the Bitcoin layers. And layers, I mean, of course, like the Bitcoin main chain, the Bitcoin blockchain itself, Lightning, Liquid, and as of somewhat recently, Rootstock. And when we talk about these layers, they have very different capabilities. On Bitcoin, you have the opcodes. On Liquid, you have also the opcodes, but in a more advanced fashion with some extra features. On Rootstock, you have pretty much the EVM. And Lightning is its own kind of completely different beast to tame with like basically no scripting capabilities. So when we want to bridge and have an atomic exchange of Bitcoin from one layer to the other, what we need to do to have like a common denominator for all of those four, what we need to do is called HDLCs. Hash time lock contracts are the only contracting primitive, the only scripting primitive that exists on all four of those. The limiting factor is especially Lightning, because the only thing that Lightning can do is send payments, and these payments are sent via HDLCs. And since that's the only thing we can use on Lightning, that's what we have to use, and that's what you have to implement. What we have to implement on all of these other layers. What do we need for an HDLC for a hash time lock contract? A hash lock and a time lock, as the name indicates. And what that basically means is a hash lock is that you lock coins in a script with a hash. And to unlock the coins, you have to show a secret to the script. Meaning that you take a secret, you hash it, you put that hash into the script, and to be able to unlock the coins, you have to show the secret to the script. And time lock is, I think, pretty clear. It can only be spent after a certain amount of time. So it's locked for a certain amount of time. And that's how all payments on Lightning work. When Bob wants to pay Carol by routing via Bob, Alice wants to pay Carol by routing via Bob, what Alice does is send an HDLC from her node to Bob's node, and Bob does, after that, send an HDLC from him to Carol, and you have this sequence of HDLCs. Carol, in the end, when she receives the HDLC, releases the secret of the hash lock, and the payment goes through. In case of some HDLC getting stuck, some node being offline, or like bad things happening, there's always the time lock component. And if the secret isn't revealed in time, the time lock is enforced and all the coins go back to where they were before. So either these scripts are unlocked via a secret, the hash locks, or after a certain amount of time, the time lock. And what we do with our swaps is we take that exact same primitive of the hash time lock contracts, but instead of forwarding the Lightning payment to a different Lightning node, is we take that HDLC and forward it on chain. We take that contracting primitive and forward an HDLC with the same hash lock and the same time lock onto the blockchain, in this case to Liquid. When you want to do that, when you want to push such a HDLC on chain, you need to write the script. And I'm gonna show the Bitcoin version of the script, but it works the exact same way in Liquid, because Bitcoin script is exactly the same as Liquid script. It's just that Liquid script has a few extra features, which we don't need for our simple HDLC example. So this script is the same for Bitcoin and for Liquid. The first iteration of the script that we did was in SegWit version 0, and that was our script. Let's go over it real quick. We have the opcode opsize, which means that the first element that we push to the script as parameter, let's get the size of that. Then we push bytes 20 on the stack. 20 in hexadecimal is 32 in like decimal. So we get the value 20 in the stack, and then we op equal, meaning the first parameter of the script has to have the length of 2. In the case, we go into the hash log segment. There's an op if. So if the first parameter of the script has 32 bytes length, we go into the if. We take that variable, hash it with hash 160, push the hash lock, the hash, onto the stack, do op equal verify, meaning that we verify that the op hash 160 of the parameter, so the hash of the parameter, is the same as the locked hash lock value that we expect it to be. And if that's also the case, we push the public key of the party who is supposed to claim the HDLC on-chain onto the stack. In the very end, after we end the if-else statement with an object sig opcode, so we take this public key and verify the signature in the end. Yes, question.
Programming language or is
Come again?
well, this is programming language or
Oh, this is Bitcoin script. This is Bitcoin script, like Bitcoin opcodes. That's what you can do with the Bitcoin scripting language. So to reiterate the concept, if the first parameter of the program has a length of 32 bytes, we check if it's correct against the hash that we expect it to be, and if so, we push the public key of the party who is supposed to claim the HDLC and verify the signature against that. That's the hash lock part. If the first parameter is not the length 32, we drop it, we just ignore it. We push the lock time as blockade onto the stack, and then do object lock time verify to make sure that the time that we expect has passed already. So this is the time lock. We drop the result of object lock time verify, and then we push the public key of Boltz so that we can get our coins back in case the other party is just not claiming their coins. That's the time lock part of the thing. But when we look at this script, it's not very efficient because for every single on-chain HDLC, we have to take this whole script, hash it, create an address for it, and when we want to spend it, we have to show the whole script, although we just execute the if or the else path. So we push a bunch of unnecessary code and opcodes to the chain. This is where Taproot helps us. And I already mentioned it that with Taproot, you can do a bunch of fancy things to avoid pushing all the data to the chain. And that's what we did. The first primitive we used is the Schnorr signatures with music 2. In the old script, we have 2 different public keys, one of the other party, of the user, and one of ours. What we do with music 2 is we have 2 keys, one of ours, one of the user, and those 2 keys we combine into a single one. We aggregate 2 keys into a single public key with this music 2 signature generation scheme. So if we and the user agree completely on what's about to happen and what is supposed to happen, we can take our 2 keys, combine them, and together sign off on a transaction. So if we do that, it looks like a normal single sig spend on-chain. It's a hidden multi-sig, and the communication happens completely off-chain via HTTP or whatever transport you want to use, and the blockchain usage is minimal because you do all the tricky stuff of coordination, not on-chain via contract enforcement, but off-chain via signature aggregation. And the other cool thing we did is that in case that we and the user don't agree, we still have to have the script in there to be able to force the coins to the destination where they are supposed to be. So we still have to have the script. But instead of having the whole script and an if and else path, what we do is we rip them apart into two different pieces and build a tree out of them. Our tree is not deep. There's just one layer to it because we only have two branches, two different possibilities to execute things. The left side is the hash lock and the right side is the time lock. And if you look closely, those two are basically the if and the else path that we had before. It's just in two different scripts now. So the hash lock and the time lock, same thing, just now in two different scripts. And when we want to spend those scripts, we don't have to show the whole thing with an if and an else anymore. We just show the part that you want to execute. So if you want to use the hash lock and prove you have the secret, you just show the hash lock script. If we want to get our coins back and execute the time lock, we just have to show the 4 opcodes and a little bit of data of the time lock and not the whole script. That also saves quite a bit of change space in the non-cooperative path in case we cannot do a cooperative signature. What we do then is combine those two. So we have the key path spend, where you have the two public keys that you aggregate into a single one with which you can spend. And that aggregated combined public key, you tweak its code, basically multiply with the hash of the tree of scripts. That means you can spend both ways, either by signing together and agreeing on what's supposed to happen, or in case you don't want to agree or can't agree because someone is trying to cheat, you can just show up to the chain and say, hey, this public key was multiplied with this tree of scripts. Here's the script I want to execute. Here's the proof that this is actually the case and the script is valid for this public key, and execute the script. So you have the exact same ways to spend as by having a whole big program, just that you can be more selective about what you want to execute, which allows you to build bigger structures and have them more efficiently, more selectively published on the chain. Only what you need needs to go there and not everything all the time. So that's how we do these swaps. By taking the Lightning primitive of hash time lock contracts and publishing them to the blockchain in the exact same way a Lightning node would forward payments to their other Lightning peers. With Taproot, we made those as efficient as possible and use as little chain space as possible by using all the latest and greatest advancements in the Bitcoin space. But what is that useful for, especially on Liquid? The one use case that we found, or rather that found us, is wallets. Just to name like the bigger ones, we have the Bull Bitcoin wallet, Aqua, and Blitz from Blake, who's going to do a session tomorrow and show you all the details on how it works and why it's a good idea, or might not be a good idea to do that, but he's going to talk about that tomorrow. And yeah, these wallets use atomic swaps with the exact tech I just went over, abstracted away from the user, and use a Liquid wallet plus the HTLCs on-chain with the scripts and whatnot to do Lightning payments without actually running a Lightning node in the app. Basically, when you have a look at, for example, Aqua, you have the Bitcoin balance, Tether, which we ignore for now, and what they call layer 2 Bitcoin, LBTC. That thing is effectively a Liquid wallet, but what UI allows you to do is, for example, paste in a Lightning invoice or scan a QR code of a Lightning invoice. And what it will automatically do in the background is create a swap with Boltz create a swap with Boltz, send from its liquid wallet to fund the swap, and we will set the Lightning payments and claim the liquid Bitcoin like a Lightning node would claim an HDLC that is forwarded via it. And same thing for receiving. If you go to receive an Aqua, select Lightning, enter an amount, and click create invoice, it will create a swap account, and all the on-chain HDLC stuff will happen behind. So basically, the entirety of Lightning complexity is abstracted away in the Aqua wallet. It feels like a Lightning wallet to the user, but in the end, it's a liquid wallet that just does swaps between liquid and Lightning when needed. And the question is, why would you want to do that? Why do you want to have swaps between liquid and Lightning? And the reason is simple. There's so many different technologies built on Bitcoin right now. You have the Bitcoin main chain, you have Liquid, Rootstock, Arcs, Fedi, Cashew, and in the end, the one thing that exists on all of them, that you can send to and from on all of these networks, is Lightning. You can swap from Liquid to Lightning. On the main chain, there's actual, like real Lightning. On Rootstock, you can swap to Lightning. Arc has a Lightning swap. Fedi and Cashew, you can go in and out with Lightning. So Lightning is becoming the common language of the Bitcoin ecosystem. Everyone interacts with each other on Lightning seamlessly, which is why this is such a cool thing for Liquid. By Liquid having swaps to and from Lightning, you can go from Liquid to anywhere else pretty much immediately and whenever need be. So that's the why. And I'm super happy about Samsung approaching us like a little over a year ago to get these swaps into Aqua, because it pretty much created a new kind of Lightning wallet that has these swaps and allows you to interact with your Liquid wallet that allows you to interact with your Liquid wallet with any of the other Bitcoin ecosystems and layers. It's pretty much the bridge from Liquid to the rest of the Bitcoin world. And in the end, I want to do a quick demo and show you on a code level how all of the key path, script path kind of things work, and go over a little bit of code just to have a clearer understanding of what's happening behind the scenes and not just these abstract overviews. All right. So yeah, I'm gonna zoom in a sec. Hold on.
what are the close?
All right. Let's have a look. We're just gonna ignore all those imports and JavaScript shenanigans, and let's have a look at the actual swap stuff and what's interesting. We're gonna use the Boltz API. That's our mainnet endpoint. And because we are playing around on mainnet, I'm just gonna swap 1,000 sats, because if it goes around, whatever. This is an address of my green wallet. Actually, let me get the new address real quick. No, the internet is really bad today. Anyways, while that's loading, we're gonna use the network Liquid, which is the Liquid mainnet. This initializes some of the libraries and cryptographic primitives to do blinding. We're gonna create our 32 bytes secret. In our case here, just 32 random bytes. And because this is not actually a wallet, but a random script. We're gonna make a random public key. Yeah, seems like the Blockstream servers. Yeah. The Blockstream servers are down right now, so I can't get into my fucking wallet. We'll just use my old address and call it a day. All right. We call the Boltz API and we want to do a reverse swap. So a swap from Lightning to Liquid. For like 1,000 sats, our invoice amount to LBTC, which is Liquid, from Bitcoin, Lightning. Our public key, we give Boltz our public key as hex string. And we give it the SHA-256 hash of our secret, but only the hash, not the actual value. Gonna console log that to see what's going on. We're gonna open a WebSocket to get updates about the swap and see, hey, something happened, that we can react to that and do necessary actions to complete the swap. Whenever we get the WebSocket message, we're gonna parse it and print it out when it's of relevant to us. When a swap is created, we send out status updates to inform the client about what's going on. For example, swap created means pretty self-explanatory. It was created. Transaction mempool is the next state we're going to be in, and it means that Boltz sent the on-chain coins and they are ready to be claimed. So the HTLC was created, and now everyone is waiting for our script here to do something and claim those on-chain coins and get them into their wallet. What we're going to do here is the signature aggregation. So we're not going to enforce the script, but we're going to do the magic 2 public keys into 1, 2 signatures into 1 aggregation thing. For that, we create a new music session. Music is the protocol that is used for the cryptographic magic to aggregate signatures. And we're going to tweak our music. So we're going to tell our music about the scripts that could be executed, but we just won't in this scenario. But you still have to tell about the music about, hey, these scripts could be in there, so be careful with that. We pass the transaction that Boltz sent on-chain, detect where in which output our swap is, error hard in case it can't find it, so hopefully that doesn't happen. And then we create a claim transaction. With the output, our keys, the pre-image, we say cooperative true because we just want to see the signature on chain. We are using taproot, spend this transaction hash, and we are blinding with this private key. We're gonna send to my destination address from above, and we're gonna blind our output with the blinding key of the address. That will give us an unsigned transaction. And the unsigned transaction we still have to add a signature to via the music and the partial signatures that we aggregate. For that, we call our endpoint with, hey, please sign the zeref index, so the zeref input of this transaction. This is the pre-image to prove that I actually know the secret. And this is my music session information. We tell the music about, hey, let's do some stuff. Let's aggregate some data. Tell it what we are going to sign. In this case, our transaction that we hash for this special music thing. We add the partial signature of the other side, sign our partial part, and in the witness of the transaction, in the input, we put the aggregated result. That we're going to broadcast. And when everything works well, we're going to get this invoice settled, a status update, which means the swap went through and everything is fine. Log that out, close the WebSocket, and end the script. And that's what we're going to try real quick. Let me try the green wallet again. Hopefully it loads this time. If it doesn't, because just gonna check it out in the Block Explorer. So we created the swap, got an invoice, and a bunch of extra information. This is the tree with the claim leaf is the hash lock, refund leaf is the time lock. And this is like the Bitcoin script as hex. A binding key, the address in which the coins will be locked. A refund key that is going to be used in the time lock scenario, when the time lock will be available and how much will be sent on chain. Swap was created just fine. Let's pay the invoice. Send. Ah, fuck. Timeout. Had that before because the internet is really flaky. Do it again. Timeout. Oh, come on. Let me switch to my hotspot. Live demos are always horrible because everything that can go wrong does go wrong. So let's try this again. Oh, come on. Am I being stupid? Oh, what's going on? Like, this works just fine. What the fuck? Yeah, the internet really hates me right now. I don't know. What I can do is maybe it's gonna work in the browser. So basically on our website, this exact same thing happens.
I think that will wrong work because I send some chat via lightly to Alpha and
Went through?
1 hour later. I think that don't work.
Really?
Yeah. I send some chat via lightning to my wallet subscription to Alpha One
Doesn't show up?
and no, it's weird. I received after 1 hour.
After 1 hour, yeah.
And my this kiwi.
Cute. Yeah, that's about a Satoshi bug. That's a
Yes.
bug about Satoshi. All right. What I can do is show it in the browser because that's gonna work just fine. Hold on. Our browser is basically, our web app is basically using these exact same libraries and doing the exact same thing, just in the browser with a nicer UI than the CLI. It's showing us the invoice, which we can pay again. Come on. Yeah. Send. And he will get to see the WebSocket updates of, hey, swap update of this ID. We're gonna claim this cooperatively, private key and pre-image, and we broadcast the transaction. Let me check out the transaction and how it actually looks on the chain.
It's not a load.
Yeah, I have not turned the Explorer though. So this thing did exactly that, claiming Taproot swap cooperatively, meaning that we did the signature aggregation and no script was revealed on the chain. Let's check the transaction. And when we look at the input at the witness, we only see these 64 bytes. And those 64 bytes are a signature. So the entirety of the scripts, the signature aggregation, there is nothing to be seen on chain. All there is a signature. And that this was a swap and all these script paths could have happened, you don't see those on-chain. All there is the aggregated, tweaked public key and a signature that spans. That's it. If the server and the client were not cooperating, you could see the script that is being executed, but since everyone is just fine with the result and everyone is happy, they can agree on the signature that spans the coins. And this saves, misclick, hold on. And this saves quite a bit of chain space because we only need to push these 64 bytes. Imagine the whole script, including the if and the else statements from the very beginning. In 100%. No, hold on. Yeah. Imagine the whole script from the beginning would have had to be pushed on-chain every single time. This is so much more data than just the signature. So using Taproot and the aggregated signature saves a lot of chain space, makes a transaction cheaper, and therefore allows for the wallet use case. If we would have to do the whole script every single time, it would be too expensive to build a wallet with. But with these efficiency gains, a wallet use case is feasible because if you send from Aqua, it's only a couple cents in fees. If you receive, it's basically 5 cents in liquid network fees. And that's only possible because we are so efficient in just needing the single signature to spend the HTLC on chain. And that's pretty much what we do on Liquid. I would have loved to show that I actually received in my wallet, but it's not loading. And I guess that's why Pablo ran off so erratically to fix that. Yeah, that's pretty much it from my side. And I'm opening the room up for questions about Bolt specifically, about scripting, but also like anything else, Liquid or Bitcoin related, to make sure that there's no open questions left for tomorrow, because there's actually going to be some coding with Blake, and let's just clear everything up today so that tomorrow everyone can follow along and code just fine. Yes.
So whenever you talk low, it's not a rich code. What were the additional features other than doing the hashing though to all your web to bulk keys?
Which other new opcodes came with Taproot or on Elements? On Elements, like, yeah, I can show the list of like new opcodes on Elements. Hold on. There's a nice markdown document in the Elements repo. The things that Elements added are the TypeScript, I think. Yeah, TypeScript block codes. The things that Elements added are a streaming SHA. So if you want to hash values bigger than the max stack size of 512 bytes, you can stream data into the SHA and have like a hash of bigger amounts of data. That's what Elements added. Then there is object from stack, which means that you can verify a signature against arbitrary data that you push on the stack, which is super useful for covenants. You have actual introspection covenants where you can check the outpoint you are spending, the asset you are spending, how much you are spending, and where you are spending to, which is basically everything that's being discussed for Bitcoin covenants. Elements has the most fully compatible, everything possible version imaginable. So basically all the covenant things are already there. You have also 64-bit multiplication, division, addition, and subtraction. So like 64-bit proper math opcodes. And some conversions, tweak verify, EC multicar verify, like pretty much every single covenant related thing that is being discussed for Bitcoin already exists in Elements, including 64-bit arithmetics.
Is that code a layer above like using all opcos will make new features, or I guess I don't know enough about opco, but I'm wondering if it's viable with like the architecture. So like I said, it's what it's them right. They were in a horn. They were
These opcodes, basically in your Bitcoin node, there's a virtual machine that executes the opcodes. Think of it like a JVM. And the JVM runs on x86, on ARM, on RISC-V, whatever. Same thing for your Bitcoin node. If you run LMNT on your machine, all the opcodes run on it because there's a virtual machine in there that executes the opcodes. And these opcodes that are added to Elements, it just means that the Elements node software supports more of these instructions in its VM than the Bitcoin node software.
I have a question about HTLCs. With the HTLCs, you always have to fix the amount, right? There's no change outputs with HTLC.
With HTLCs, when you claim them, when you when you enforce them by claim or true, you always do the full amount. What you can do is batching, meaning that you can enforce multiple HTLCs in a single transaction so that you have a bunch of inputs of different HTLCs and a single output for like batching and efficiency. But in theory, it's always a self-spend because you go from the HTLC that you are allowed to spend to a wallet address that you actually own by just public-private key, which is like a sensible thing to do.
Maybe you can explain the differences between liquid script, tap scripts. Like
I know where you're going, yeah.
on a very high level.
So basically, what we had is Bitcoin op script that the Satoshi invented in the first version of Bitcoin. That's what we call like Bitcoin opcode scripting. Then we did SegWit in 2017, which changed which fixed a few minor bugs in the opcodes that Satoshi invented. With SegWit version 1, also known as Taproot, we got TapScript, which is basically the same thing as Bitcoin scripting way back in the day, but with another few bugs fixed. And with every new SegWit version 0, SegWit itself, SegWit version 1, Taproot, new opcodes are enabled. Like for example, with Taproot, the old object multisig opcode was removed, and there was a nice, cleaner implementation added. So basically, we have different versions of Bitcoin script, namely Legacy, SegWit version 0, and SegWit version 1. And it's the same thing. It's mostly backwards compatible, just that the newer versions are a little bit cleaner and have bug fixes of the old code that Satoshi created way back in the day. And Liquid did change a few things in its TapScript, so SegWit version 1, the scripting language for Taproot, to like add the covenant features and the 64-bit arithmetics. So you have legacy Bitcoin script, SegWit version 0, TapScript SegWit version 1, and the Liquid version of that has some extra features. But in the end, it's full backwards compatible. Because if you, for example, take, I don't know, op inspect version is redefined as op success. So if you just take op inspect version and execute on the Bitcoin main chain, it will just say success and everything's gonna work. But like if you want to enforce those things, you need to use the right version. It's like upgrading your, I don't know, your computer from Windows 7 to Windows 10. Everything still works, but there's going to be new features that you can use.
Where are these what kind of use cases were you seeing?
For new use cases with covenants. Like the biggest thing that immediately comes to mind is Arc. Arc is like a new Bitcoin layer 2 And this new layer 2 is going to be much better if a covenant is enabled. Actually, the Arc Labs guys who are building the implementation did the first demo on Liquid because Liquid has covenants already. So it's really useful for prototyping and for like less interactive layer 2s. They are going to have covenants. And also, like, if we ever get covenants on the main chain, Lightning is going to get much better. In like 2018, Christian Decker proposed a new version of the Lightning network called L2, which is going to be so much better in every single aspect. But the one crucial piece it's missing is a covenant. So basically, you can build everything you want without covenants. But if you have a covenant, it makes the protocol less interactive. So you don't have to exchange half-signed transactions all the time. You can just let the script with a covenant take care of the spend condition and don't have these half-signed transactions you need to store until the end of time.
Can you explain how water works? I know that.
Yeah, it's super tricky and nobody knows exactly how it's gonna work.
No.
But I can give the high-level rundown. So imagine all of us in the room are using the same arc, and everyone in the room has like 1 Bitcoin in the arc. When I want to send you some of my Bitcoin in the arc, what I do is I give up the right to my 1 existing Bitcoin, create my change output. Let's say I want to send you half a Bitcoin, create the change output for my half, and the other half goes to you. And everybody just sends each other Bitcoin. We're giving up the rights to get the ones that they own right now for new outputs. But none of these transactions, none of these new outputs are actually sent to the blockchain. What the Arc does is it creates such a taproot tree of different paths, different scripts, and these different scripts say who owns what. So basically what the Arc does is a big batching engine. Instead of publishing all transactions to the blockchain, it creates a big tree of who owns what, and all these state updates happen at the same time. So basically, instead of everyone broadcasting a transaction, the Arc server aggregates them all, compresses them into a single output, and that's the new state of the Arc and the ledger of who owns what. If you want to force your coins out of that single output, you show up with the script and the path, how to prove that the script is in there, and get your coins back. So it has unilateral exit, you can't force your coins out, and it's basically a big batching engine of all the transactions that happened since the last batch get updated in the tree of scripts. I hope that made sense. It's still very raw in the spec, and nobody knows exactly how it's going to turn out. But basically, imagine it as a big batching engine of every hour we aggregate all transactions that happened in the Arc into a single output that has hidden ownership proofs. It's like still like nobody has seen an actual Arc in production yet, so it's more of an idea than a real world use case.
You're saying you can prove the tree.
Basically, yeah. Like with Taproot, you have all these scripts, but you can't just show up with a random script to the chain and say, here, give me money, please. You have to prove that, hey, when this output was created, this script was in the tree that the public key was tweaked for. So you have to prove that, hey, this script is not made up, but it was actually included in the output when funds were sent to the output. That's what I mean by proof.
I can see that one.
Yeah, like Arc is pretty crazy stuff. Like if you have an HDLC with like 2 paths, sure, it's fun in games. It's like imaginable. With an Arc, when you have lots of people using an Arc, you have like 50 layers of tree structure, and yeah, it gets pretty complex and nobody knows exactly yet how it's gonna turn out. So yeah, I'm really optimistic on Arc, but for the time being, if you wanna use like a simple Lightning swap thing, Liquid is still the place to be, because like ArcNode, the software for it is like still join the wait list. maybe we'll launch sometime. So it's not ready yet.
Kind of unrelated, but is Boltz planning on doing USDT swaps between Lightning and Liquid?
Tricky question. Like, we are thinking about USDT. The one reason for which we have the assets that we have on Boltz, meaning main chain, Liquid, Rootstock, and Lightning, is that we can get in and out of those networks on our own. So you can like peg into Liquid, peg out of Liquid, open Lightning channels, close Lightning channels. If you want to go like USDT from Taproot assets or Ethereum to Liquid and whatnot, you cannot do that yourself. You pretty much have to ask Tether or Bitfinex to please do that for you. And I'm not super comfortable being at the mercy of Bitfinex to run our business. But for these assets we have, we can just like close a Lightning channel, have our coins back. Peg it off Liquid, have our coins back. If we do USDT on Liquid and have a bunch of Liquid USDT, we pretty much have to ask Bitfinex to please convert that USDT to USDT and Ethereum or Taproot assets. So we would be completely at the mercy, and I'm not super comfortable with that. So maybe one day, but not anytime soon. We're gonna focus on the Bitcoin layers and stay Bitcoin only for the time being. I guess we're pretty much done for the day then, yeah?
What language is your library on the blocks? Library.
We have JavaScript, our reference, Rust, Python, Dart, C++, and some bindings for other stuff too. But it's mostly like we ourselves use JavaScript and Rust.